Hi everyone, this is Mrs. GA, and today we're going to talk about dependent events. Alright, I have a quick warm-up for you guys, so please pause the video and give it a try. Alright, so there's actually a few different ways we can check to see if these are independent events. And these events, no matter which way you do it, we can show that they are independent. So in the last lesson we learned one way to show this is by showing that the probability of A given B is equal to the probability of A, or the probability of B given A is just the probability of B. So essentially saying the condition doesn't affect the probability of the event. Or you could show that the probability of the intersection of events A and B is the product of the individual probabilities. So you could see here that I found the individual probability. So the probability of being right-handed is 22 out of 25. Or you could see I did 220 over 250. And the probability of playing a musical instrument is 50 over 250, which is 1/5. The probability of the intersection is 44 out of 250, which is 225 over 125. So if you take the product of the individuals, it does equal the product of the intersection. So that would be enough to show that they're independent. Or you could find the conditional probabilities. So the probability of A given B, so again, the condition is that they're a musical instrument. So it's 44 over 50, and that is the same as just the probability of A, right? 22 over 25 is equal to 22 over 25. Or you could find probability of B given A. So again, in this case, being right-handed is the condition, and so it's 44 out of 220, which is 1/5, which is the same as just the probability of B. So I actually showed it that it's independent in 3 different ways. So whichever way you did it is fine, but it's good to have multiple ways of checking to see if something is independent. So today we are going to be focusing on dependent events. So this is when the occurrence of one event affects the occurrence of another. So essentially, dependent events are events that are not independent. So we can, to test for dependent events, we are essentially trying to show that it fails the test for independent events. So here's just a recap of what we did in the warm-up. You could either show that the probability of event given another event is the same as just the probability of that event. So again, the condition doesn't affect that probability. Or you could show that the probability of the intersection of the two events is the same as the probability, the product of the individual probabilities. So if you test these and it fails the independence test, that means that they must be dependent. So let's try this for one more time. We're going to look at this table of data, and we're going to try to determine if the events are independent or dependent. And I'll do it in a number of different ways, so just like we did in the warm-up. So first we have event O, which is that a person prefers walking outdoors, and event M is the event that a person is male. So here's event O is walking, they prefer walking outdoors. I'll highlight these in red. And event M is that they're male. And here's the intersection right here. I'll highlight it in gray. And here's the total number of people in the survey. So let's start by finding the individual probabilities. So let's find the probability that they prefer walking outdoors. So outdoors, 60 people prefer walking outdoors out of 100. So that's 3 out of 5 probability. Now let's find the probability that they are male. So there are 50 males out of 100. So it's 1/2. And now, this should have said O and M. Let's find the probability of the intersection of events O and M. So there's 40 people that are both male and prefer walking outdoors. So it's 40 out of 100, which is 2/5. So one way we can check to see if these are independent or dependent, again, is by seeing if the product of the intersection or the probability of the intersection is equal to the product of the individual probabilities. So is 2/5 equal to 3/5 times 1/2, well, 2/5 is not equal to 3/10. So just this alone, we can say that this is not true. So we can say that they are not independent. And I guess instead of saying, we could say not independent, but if two things are not independent, that means that they are, therefore, dependent. So these two events are dependent. Now let's try showing that in another way just for practice, or maybe you prefer doing it in a different way. Let's find the probability of event O given M. So the condition is that they are male. So there are 50 males. And the probability that they are male given that would be 40 out of 50. Sorry, that they prefer walking outdoors given that they are male is 40 out of 50, so 4/5. So you can see that the probability of O given M is not equal to the probability of event O, which is 3 out of 5. So since they are not equal, again, this would be a way we could say not independent. So it also shows that they are dependent. Or we can even do the same with the probability of event M given O. So if prefer walking outdoors is the condition, that means that there are 60 people that meet that condition. And of those, 40 of them are male. So that's 2/3. So we can see that the probability of M given O is not equal to the probability of M, which is 1/2. So again, we're showing in a third way that these two events are not independent and again are therefore dependent. So any way that you want to do this is fine, but again, it's good to know different ways of approaching this problem. All right, so once we know that two events are dependent, we can find the probability of those two, of the intersection of those two events using what's called the multiplication rule. So again, we are assuming that we already know that events A and B are dependent. So the probability of A and B happening is the probability of A times the probability of B given A. Okay, so I have said in the past, if we are doing something, and means multiply. So we're still multiplying two probabilities, but because they are dependent on each other, it's the probability of A times the probability of B given that A has occurred. And it makes sense if two things, if one event affects another, then that event should be a condition of the other one happening. All right, so let's see if we can use this multiplication rule to help us find some probabilities. So here we have 5 tiles with the letters A, B, C, D, and E in a bag. So we choose a tile without looking, and then we put it aside, and then we choose another tile without looking. So since we are pulling a tile out of the bag and then putting it aside, when we go to choose that second tile, there are fewer things to pick from, and there could be fewer favorable outcomes for us. So what we did in the first pick affects what happens in the second pick. So here we don't need to test this, it's just logic that these two events are dependent. Okay, what happened in the first pick affects the second pick, and this is only because it had this key phrase that we put it aside. We didn't put it back in the bag. So first we want to find the probability that we chose a vowel followed by a consonant. All right, so let's call choosing a vowel event V, and let's call choosing a consonant. Choosing a consonant, we'll call that event C. So if we want to find the probability of the intersection of events V and C, we're going to be doing the probability of V times the probability of C given V. So let's see if we can find those individual probabilities. So first, picking a vowel. Well, there are 5 total outcomes because there's 5 letters in the bag. And for vowels, there are 2, so there are 2 favorable outcomes there. And now we're going to find the probability of choosing a consonant given that we have chosen a vowel. So if we have chosen a vowel, again, we've picked a letter, so that decreases the number of letters left in the bag. And if we are assuming that we chose a vowel, okay, we're taking out either A or E, but there are still 3 consonants left. So we know that there are 3 favorable outcomes there. So we do 2/5 times 3 over 4, and then that gives us 6 over 20, so a probability of 3 over 10. All right, so now let's look at part B. So here, find the probability that you choose a vowel followed by another vowel. So I'll call this event V, and maybe I'll call this like event A, meaning another vowel. So it's not the same event twice, again, because these are dependent events, and the second pick depends on what happened in the first pick. So let's find the probability of V given A. So we're going to find the probability of picking a vowel times the probability of picking another vowel given that we picked a vowel the first time. Sorry, that should be a vertical line here, given that we picked a vowel the first time. So the probability that we pick a vowel that first time is still 2 out of 5. There's 2 vowels out of 5 possible tiles. And then here we're finding the probability that we pick another vowel, again, assuming that we already picked a vowel. So since we already picked something and we haven't put it back in the bag, that's decreasing the number of total outcomes by 1. But also, we are assuming that the tile we picked is a vowel. So we're actually eliminating one of these 2. It doesn't matter which one, but there's 1 fewer favorable outcome here. So here we actually have a probability of 2 out of 20, or 1/10. And there you go. All right, so I have one for you to try on your own. So please hit pause, and then when you're ready to check, you can hit play. All right, go ahead and check your work here. So again, the key phrase that makes these 2 events, or these events, dependent is the fact that you put aside the marble that you pick. So actually, if you put that marble back in the bag after you pick it, then the first and the second pick are actually independent. So putting it aside is a really key phrase here. So finding the probability that you choose a white followed by a blue, so the probability that you choose a white the first time is 4 out of 6. And then you need to find the probability that you choose a blue, given that you've picked a white. So the fact that you picked a white and didn't put it back changed the total number of outcomes from 6 to 5, but it didn't change favorable outcomes for blue because there are still 2 blue marbles left. And then you multiply and simplify, you should get 4 out of 15. Now for part B, probability you choose a white the first time is 4 out of 6, and then the probability that you choose another white, given that you already choose a white, well, that affects the total outcome and the favorable outcomes, because there's 1 less total marble, but there's also 1 less white marble. So you multiply, simplify, and you should get a 2 out of 5 probability. All right, so now we're going to talk about how we would find the probability of 3 or more dependent events. So to do this, we kind of just take our dependent event formula and kind of extend it out. So if you're finding the probability events A and B and C, and all of those events are dependent, you find the probability of A, and then the probability of A given, or probability B given A, and then the probability of C given A and B, and again, you can extend that out for as many as you want. So it'd be the probability of the next event, given the that the other 3 events have occurred. So you can kind of just extend this formula for as many as you need. So this example says you have a key ring with 7 different keys. You're attempting to unlock a door in the dark, so you start trying keys 1 at a time, at random, and you keep track of the ones you've already tried. So when we say you keep track of the ones you've already tried, you're kind of eliminating them from the keys you would pick. So it's kind of like removing it from the bag with the previous examples. So since you're taking away outcomes, this makes each of these events dependent. So what you did on the first one changes the probability of the second the second try. So here we want to find the probability that the third key you try is the right one. So the third key is the right one, which means the first two are wrong ones. So we're essentially finding the probability that you picked wrong. So I'll call it W1, and then you picked wrong again, so W2, and then you picked right. So I'll call it the probability of W1 and W2 and R. So we're going to start by finding the probability that the first one was wrong. Okay, so there's 7 possible keys to pick from. And we're assuming that only one of those keys is right, so that means that there's 6 possible wrong keys that you could have tried. So 6 out of the 7 are wrong. All right, so now we need to multiply that by the probability that we pick another wrong key, given that the first key we picked was also wrong. So now, again, we've tried a key, so now we have only 6 left to pick from, and we're assuming that the first one we tried was wrong. So we've tried one of the wrong ones, so we have 5 wrong keys left to pick from. So this event affected the favorable outcomes and the total outcomes. And then last, we need to find the probability that we pick a right key, given that we've already picked 2 wrongs. So for this, again, we've already tried 2 keys, so there's only 5 left to pick from. But there's only 1 favorable outcome for right key. There's only 1 right key on your ring, so this is a 1 out of 5 probability. And then you just multiply across the numerator and denominator, and you simplify it, and you get a probability of 1 out of 7. All right, let's look at part B. Find the probability that one of the first 3 keys is right. Okay, so there are a few different ways we could approach this, but one way of thinking about this is for finding the probability that one of the first keys is right, we can actually use the complement. So the complement of one of the keys being right is not one of the keys being right, which would imply that they are all wrong. So the complement would be that all of the first 3 are wrong. And then if we find the probability of the complement, we could subtract that from 1, and that will give us the probability that one of the first 3 is right. So for the complement, again, we're going to find the probability of wrong, and then another wrong, and then another wrong. So I'll call it W1, W2, and W3. So the probability that the first one is wrong is 6 out of 7. And then the probability that the second one is wrong, given that that first one was wrong, is 5 out of 6. Again, there's 1 fewer to pick from and 1 fewer favorable outcome. And then the probability that the third one is also wrong, given that the first 2 were wrong. So there's 4 out of 5 because there's 1 fewer wrong and there's 1 fewer total. So if you multiply these and you simplify, you get 4 out of 7. But remember, that's the complement. So the probability that one of them is right would be 1 minus 4 over 7, which is a 3 out of 7 probability. So another way we could have approached this problem is kind of looking at each individual outcome separately, so saying this or this or this. So if we're finding the probability that one of the first 3 keys is right, there's really 3 things that could have happened. It could have been right on the first pick, or it could have been wrong then right, or it could have been wrong then right. So if it's this, or this, or this, we would find these 3 individual probabilities and add them up. Because remember, if we have something, or means add. So to find the probability that the first pick is right, well, there's only 1 favorable outcome out of 7. And then to find the probability that it is wrong and then right, and again, these are dependent, Well, first we do the probability that it was wrong. So there's 6 wrong out of 7 possible. And then the probability that it's right, given that the first one was wrong. So there's 1 favorable out of 6 left to pick from, because again, we've already picked 1 wrong key. And then the probability of wrong and right. So the first one is wrong is 6 out of 7. And then the second one is wrong. Well, there's 5 out of 6 because we've already picked 1 wrong one. So there's 1 fewer favorable and 1 fewer total. And then the third one is right. Well, there's only 1 favorable outcome, but now there's only 5 left to pick from. And so these are the 3 individual probabilities. So we're going to add them up. So it's 1/7 here. And then if you simplify this, it's 1/7 again. And then if you simplify this, it's 1/7 again. And if you add those up, you get 3 out of 7. So again, kind of 2 different ways to go about this. Either way is totally fine. But this is actually a nice little review of when we did something or something. So remember, or means add, and means multiply. So again, this was a nice little review of a slightly different concept within probability. Okay, I have one last one for you to try on your own, so please pause the video and give it a try. All right, go ahead and check your work here. So for this first one, you can see that if they're all 3 white, not only does the total outcomes decrease, but the favorable outcomes decrease as well as they're being used. So 4/6 times 3/5 times 2/4. And then for part B, this one's a little tricky. So if you're just finding the probability that 2 of the customers get silver cars and 1 gets white, it doesn't matter what order that happens in, but you have to consider all of the possible orders. So that could be meaning silver, silver, white, or silver, white, silver, or white, silver, silver. So you have to consider all 3 of these possibilities. And then for each of those individual probabilities, it's all 1/15. So you see that the numbers in the numerator and denominator are the same. They're just in different orders. So each of those individual ones has a probability 1/15. But since it's an OR problem, then you have to add up those individual probabilities, and you get 3/15, which is 1/5. All right, that's all for today's lesson. Thank you so much for watching.